Hey everyone, good afternoon. We're running slightly late maybe, but welcome to the DockerCon 2019 Open Source Summit track on Kubernetes. I'm Deep Debroy, I'm an engineering manager here at Docker Inc. And we're going to go over a sequence of talks led by various folks either leading different initiatives in the space of Kubernetes or actively engaged with the community. So here's a quick agenda for the afternoon. We'll be starting off with Michelle Au from Google. She leads the SIG storage. She's a key member in the CSI community within Kubernetes, and she'll be talking about CSI, some of the important updates in that area and the future. Next, we'll be seeing an interesting demo by Roberto around how to use software-defined storage on Kubernetes using open source components, specifically Rook and Ceph. Next, we'll be going back to networking, and Arco will be showing us how to deploy Istio as an ingress controller. And finally, we'll be wrapping up with some updates around Windows support that just became GA in 1.14 and the future in that space. So with that, I would like to hand it over to Michelle.
All right, thank you, Deep. Yeah, like Deep said, my name is Michelle. I am a software engineer at Google, and I'm going to be, I'm also a member of the Kubernetes Storage Special Interest Group, and I'm going to be talking about the Container Storage Interface, also known as CSI, and how Kubernetes integrates in with it. So I'll start with some background on the CSI project. And then I will go into what features of CSI are supported in Kubernetes. And then I'll talk about what we're planning on adding in the future, and then ways to get involved in the project. So at its very basics, the Container Storage Interface is a specification for orchestrating control plane operations for file and block storage systems. Specifically, it defines a set of APIs to do control plane operations such as creating and deleting volumes, attaching and detaching them to nodes, mounting and unmounting their file systems, and taking snapshots of them and being able to create new volumes from those snapshots. What's unique about CSI is that this is an industry standard that is developed and supported by multiple container orchestration systems, including Kubernetes, Docker, Mesos, Cloud Foundry, and potentially even others out there that I don't know about. So there's a lot of benefits for having this industry standard. First, from a storage vendor's point of view, now they can write one driver against one API and have that work seamlessly across multiple orchestration systems. And compared to the old way of developing volume drivers in Kubernetes, now vendors are free to develop outside of the Kubernetes core code base and be independent of the main Kubernetes release cycle. In addition, if some storage vendor has some core IP in their driver, they could even choose to keep their driver closed source. From the Kubernetes point of view, there are also many benefits for being able to have vendor code outside of the repository. From a security standpoint, the fewer dependencies that the project needs to take in, the whole code vulnerability surface decreases. From a reliability standpoint, now there's fewer code that can possibly crash the core Kubernetes components. For example, if you're running Kubernetes on one cloud provider's cluster and someone ends up trying to invoke functionality of a second cloud provider, you don't have to worry about potentially that second cloud provider's code crashing your own components. In addition, now the Kubernetes maintainers don't need to spend as much time reviewing vendor-specific code for storage systems that they may not necessarily be experts in, and instead leave all of the development to those appropriate experts. That gives them more time to focus on the core features in Kubernetes that can be beneficial to all the users. So all of these benefits end up trickling down to Kubernetes users. As a result of making it easier for vendors to develop their own drivers, now users have a large ecosystem of drivers available to them to use in Kubernetes. So as of yesterday, there were over 35 different CSI drivers written and tested against Kubernetes. In addition, now that vendors are free from the Kubernetes release cycle, they can release bug fixes and new features in their drivers faster without having to catch the Kubernetes release train, and also not requiring users to have to upgrade their Kubernetes clusters to get those fixes. All right, so now I'm going to switch over to sort of a high-level overview of where CSI fits into the Kubernetes stack. We have the users' workloads that sit on top, and they use Kubernetes APIs such as pods and services and persistent volume claims. And what ends up happening is the internal Kubernetes controllers will figure out which CSI driver the application is requesting, and then appropriately funnel those volume calls over to the correct drivers. So from a user's perspective, they can still continue using the same Kubernetes APIs that they do today to access their storage. And now they have this whole ecosystem of drivers that they can choose from. To go into more specific detail, the two main Kubernetes objects that are used to configure storage, one is on the administrator side, and this is the storage class. This is where the administrator will go ahead and install the CSI drivers that they want to support in their cluster, and then they create these storage class objects that contain basically the configuration and the configuration information for that driver. So before, in the provisioner argument, you would give the name of some in-tree Kubernetes storage driver. Now the only thing you change here is you just specify the name of the CSI driver you want to use, and each CSI driver is going to have its own set of parameters and configuration arguments that it supports, and all the administrator needs to do is just configure them all in the storage class. And now Kubernetes users are free to use these storage classes in their pod objects and stateful set objects. So their main interface to storage is the persistent volume claim object, and this is the since this is the user-facing object, it's important that this object remains portable so that users can take their pod and claim objects and they can just drop them on any cluster, on any environment, and they can still, they'll end up using whatever storage is available in that cluster, but they don't have to encode specific details of that storage system in their specs. It's up to the administrator to define the appropriate storage classes to abstract out that information. All right, so that's a quick overview of how CSI integrates into Kubernetes and how Kubernetes users end up accessing them. Now I'm going to go into just an overview of all the features of CSI that we support. So in Kubernetes 1.13, we announced that the basic CSI support is GA in Kubernetes. The basic functionality that we support includes dynamic provisioning, attaching and detaching, and mounting volumes. It's important that we added, for GA, we added support for the CSI 1.0 specification. This gives, because it's now 1.0, we have backwards compatibility constraints that we need to follow and make sure that users and vendors have a smooth upgrade process and can rely on upgrading Kubernetes or even upgrading the driver without having anything break. And so in addition to all these GA features, we had a number of alpha features in flight at this time. The first alpha feature is snapshots, which gives the ability to take snapshots of your persistent volume claims and then create new persistent volume claims from those snapshots. The second feature is raw block, which lets a container access the raw block device of a disk instead of accessing a formatted file system. So this is useful for some use cases for including like databases and distributed file systems that might have to manage the raw block devices themselves. And the third alpha feature we added was topology, which is the ability to restrict volumes to specific nodes, groups of nodes in the cluster, such as restricting volumes to be only accessible from certain zones, certain racks, or certain nodes. And in Kubernetes 1.14, we went ahead and promoted those raw block and topology features to beta, and also added some new alpha features, including the ability to resize your persistent volume claims, and also a feature that we call the migration of in-tree plugins. So this is an interesting feature. It's basically allowing us to delete all the in-tree vendor plugin code, but still retain the in-tree APIs that people can use to access volumes. What basically happens under the covers is that every volume call gets substituted out to the appropriate CSI driver. It's an interesting feature because as Kubernetes users, you shouldn't notice that we've done this. If we did everything right, everything should still work and nothing should break. But you still get benefits. So, by being able to migrate everything to the CSI plugins and being able to remove all that vendor code from core Kubernetes, you get benefits of a smaller vulnerability surface and also improved stability of the core Kubernetes components. So those are all the existing features that we have as of Kubernetes 1.14. We are currently in the middle of the Kubernetes 1.15 lifecycle, and we have a whole slew of new alpha features that we are planning on adding. The first feature is ephemeral volumes. So this lets you specify a CSI volume directly in the pod, and it's going to follow the pod lifecycle. So this is different from the standard model of using a persistent volume claim, and this makes it useful for a lot of use cases where you don't actually need the data to be persisted between pods or even across pod restarts. So some useful applications I've seen for this are things like supporting secrets for third-party secret stores, and also using data caches for some specific ML data sets. So those are some interesting applications for that. We're also looking at expanding the current snapshot functionality to support group snapshots, which lets you atomically take snapshots across a set of volumes. And then application snapshots, which allows workloads like Cassandra that might have their own special snapshotting functionality to also be invoked. And then there's volume cloning, which gives the ability to create a new volume from a copy of an old existing volume. So this is useful if you want all of your images to be based off of the same volume, and then all the new containers that you create from it will be pre-populated with this data. And lastly, we are starting to investigate Windows support for CSI. Right now, CSI depends on a couple of Linux-specific features, such as mount propagation and privilege containers. So a lot of this effort will be around investigating how we can support CSI in Windows, and maybe Deep will talk about this later at the end. So I mentioned there are a lot of benefits of moving to CSI, mostly around increased velocity. Now that vendors can release their drivers independently of the Kubernetes release, they can release bug fixes and new features faster. But at the same time, now there's more added challenges of moving towards this new decoupled model, namely around having to deal with versioning between the driver and Kubernetes, and dealing with being able to upgrade and downgrade those drivers independently of Kubernetes, but still retaining backwards compatibility. So this is a new effort that we are starting to look at as well, to try to make this easier for Kubernetes administrators. Some Kubernetes distros are already sort of trying to solve these problems by pre-packaging and managing the drivers that they've qualified. But here, as part of this initiative, we're trying to see if there's a more general solution that we can do that can benefit everyone. All right, so if any of these new features or initiatives interest you, there are a lot of ways that you can get involved with the project. The most important way is to join the Kubernetes Storage Special Interest Group. We are the owners of the CSI integration, and we have a very large group of diverse contributors from all sorts of different companies and backgrounds, so we would love to have you join us. We have bi-weekly meetings, and you can find all the details over on our SIG storage page in the Kubernetes community. We also have a Slack channel where we have some of the members that are pretty active there and can help answer questions if you run into any issues, or you want to get started with contributing. You can also feel free to reach out to me directly on GitHub or Slack, and I would be happy to hear about your experiences and try to find places for you to get involved with. For first-time contributors, I think some easy ways to get involved are around improving the test coverage that we have. As you've seen, we have a lot of new alpha features and beta features that we are in the middle of developing. And also, if you're interested in just looking for bugs to fix, we use the help wanted label on GitHub. So we have two main repositories, the Kubernetes CSI repository and the Kubernetes repositories. So you can look for issues with the help wanted label there as well. All right, and with the remaining time, I can open it up to any questions. Yes.
Have you guaranteed that the driver doesn't impact Kubernetes?
Sorry, can you repeat that?
How do you guarantee that the driver will not impact the stability of the Kubernetes?
Okay. The question was, how do we make sure that a driver cannot impact the stability of Kubernetes? So previously, the way that the drivers worked were that they were built directly into Kubernetes binaries. And now with the CSI driver model, the drivers are deployed as separate pods in the Kubernetes system. So now they are containerized and isolated from the other Kubernetes core binaries. So if the driver crashes, it's just that driver pod that's crashing off in its corner, but the rest of Kubernetes is unaffected. All right. Oh, there's a question in the really far back. Maybe, do we have someone with a mic that can run back there?
No, I will bring it to you. Yeah, so thanks for the talk here. I'm curious if other people have this use case. I'll just mention it. So some of these capabilities start to make it really possible to use storage volumes that are within the container infrastructure and that are also outside the container infrastructure. And so my question is whether it's on your radar to try to integrate some kind of user namespace functionality to do essentially to map UID namespace into some other UID for a legacy storage volume to kind of make it easier for container and non-container infrastructure to work with the same underlying shared volume, if that makes sense. I don't know if people are doing this. We're doing this where you have a storage system and you access it with container and non-container infrastructure, and namespaces make it very messy.
Are you saying something like you might have an NFS that sits outside of the cluster and the UID system that it uses is different from the UID system used in Kubernetes?
Yeah, exactly it. So basically using user namespaces maybe within a driver framework like this to, instead of squashing everything down to like an NFS nobody like we've traditionally done, using something like user namespaces to squash the UID namespace of a container into some other UID that is maybe being used for outside of container IO to the volume.
Mm-hmm. Yeah, that's a really good question. So there actually is a project in Kubernetes around how to integrate user namespaces. And one aspect of that project will be to figure out how we can map it to the different types of storage systems that we do support, including both inside Kubernetes storage systems and outside. So if you're interested, the SIG node is the group in Kubernetes that is driving that project. So you can go ahead and join their meetings and check out how their design proposals and stuff. All right. I don't see any more hands, so I think we can move on to the next session. All right, thank you.
Thanks everyone for joining us today. So my name is Roberto. I work at Docker in the growth data team. And today I'm going to talk about how to deploy stateful applications on top of Kubernetes using Rook. So as Michelle explained, we have now the CSI plugin or CSI interface that we can use to deploy this storage backends. And they are all containerized. So that's a big win. You don't need to worry about the way that Kubernetes release their own release cycles. So today I'm going to showcase how we deploy Jenkins with Rook and using the CSI plugin interface. And for the purpose of this talk, I'm going to use Jenkins, but you could use any other stateful application like WordPress or any other. And I will cover, as part of this demo, how Jenkins will behave when we bring down the node where the master is running with the disk attached. And so for this solution, we are going to use a shared file system that's running using the CSI interface, and they are running pods, and I'm using Ceph. So we're going to go through what is the motivation, what is Rook, and what is Ceph and CSI and CephFS, which is the shared file system. And then we're going to show the architecture, the demo, and the demo I recorded the demo because it takes time for the Kubernetes to recognize when the EC2 instance is down, and it takes some time, so I recorded the demo. And then I'll talk about the next steps for the project and also for Rook. So the motivation, so at Docker we use Jenkins to deploy or to run our CI/CD pipelines, and we also use for our ETL jobs. And every time that a node gets rotated by infra, or if the node dies, we need to manually attach the EBS volumes to this new node that comes up, and that's a manual task that we have to do today. And the goal of this project was to leverage this software-defined storage cluster or cluster, and use this to deploy to run these stateful applications like Jenkins. So the idea was to automate the storage device management, deploy Jenkins on top of that, and leverage the CSI interface. And then all the components are containerized, and then we would apply this Rook operator pattern that Rook uses that will do most of the ops work of attaching, deattaching, and managing the underlying storage backend cluster. So what is Rook? So Rook is an open source project, is very recent, but it applies this operator pattern that is very powerful. So basically it watches the cluster, the Kubernetes cluster, and every time that there are new nodes in the cluster that has a disk attached, and if the disk is free, there are no mounts, or there are no one is using that disk, it will automatically add that to the cluster. And in this case, I'm using the Ceph cluster to create this shared file system, and this is done through this extended CRDs, which are custom resources definitions that Kubernetes exposes. So you can extend the Kubernetes API using these different types and controllers, and Rook takes advantage of that and creates this new capabilities. And it's important to mention that Rook is just like an operator that's managing this storage backend cluster. So if Rook is down, it won't impact your access to the data and your cluster itself. So as I mentioned, it makes easy for us to deploy this storage cluster. And in this case, I'm using Ceph, and it's constantly monitoring the storage cluster to make sure that all the nodes are in use. And if one node is down, it will automatically react, or if you create a new node, it will automatically add to the cluster. And all these components are treated as normal Kubernetes components, so as any other stateless application or any other application running on Kubernetes. So that's running inside your Kubernetes cluster, and you can create a separate cluster or within the same one. It doesn't matter. What is important is that all the components are containerized, and you can treat them as normal pods. And Rook leverages the Kubernetes constructs to make sure that this cluster is always up to date. So if you add a new node, they will leverage this daemon sets. That daemon sets, Kubernetes makes sure that each pod is deployed in each node. And then these daemon sets will, okay, now there's a new node, so I'm going to make sure that if this node has a new device, disk device, I'm going to add that to the cluster. So Rook is managing and doing that for you automatically. And this is the architecture. So as I mentioned before, it leverages all these constructs that Kubernetes exposes. And most of the common patterns or tasks that you have to do manually to manage, like a normal disk or ABS or SSD disk, Rook will be managing for you using these constructs. And in this case, I'm using Ceph, but as you can see, you can have any backends, like have NFS or NVM, so you can choose what you want to use. And as you can see here, we have the CSI plugin that is actually being mounted into the kubelet itself. So what is Ceph? Ceph is the actual cluster. So Ceph is a distributed storage cluster, and with Ceph you can create object storage, you can create block storage, file system, and this cluster is composed by 3 main components. So one is the OSDs, which is the storage, the object storage daemon, which is an abstraction layer on top of the logical disks. So basically you have like a software-defined storage disk, which is implemented by these OSDs. You have the monitors, which is responsible for maintaining the cluster membership, and it uses Paxos. So it's another cluster on top of the Kubernetes cluster. So Kubernetes uses not Paxos, uses Raft, and this cluster uses Paxos, which is an old one. And then we have the manager that are responsible for measuring, keeping track of the runtime metrics, the cluster state, the storage utilization, and this is the actual like a cluster that Rook is managing. And here's on the right side you can see the requirements, the minimum requirements. But since you are running this on top of Kubernetes, you don't need to worry about this as long as you have like your worker nodes with these minimum requirements, which is basically like 1 gigabyte and 1 terabyte of disk if you really want to create a real cluster. And Michele already explained what is this CSI, but so here we are using the CSI Ceph driver, and this implements the provisioning, the attaching, and the mounting interfaces. And these are different pods that are running on the cluster, on the worker nodes. And this will be used to create the shared file system, which is in this case the CephFS. But you can also use this to create an RBD, which is the Ceph's Rados block devices. So CephFS is the actual shared file system. It's a POSIX compliant. It uses a Ceph storage cluster to store its data, and it has 2 main components. One is the metadata server that exposes this POSIX semantics, and it manages the read and writes across the different logic disks, and these logic disks are abstracted out by these OSDs. And the data pool talks directly to these OSDs, which then writes to the logical devices. So basically, it's a pool of disks, and you treat them as one thing. And that's the main concept about Kubernetes as well. So this is the architecture for this project. So I put together Kubernetes cluster using Docker Enterprise. With Docker Enterprise, we have a Docker cluster create command, and this, in this case, I selected 3 masters and 3 workers, and they are automatically created in 3 different regions. So I have a highly available Kubernetes cluster running on AWS, And to go deeper into the worker nodes, I have these things running there. So basically, we have the Rook agent that's running as daemon set. So as I mentioned, you have one pod per node running, and you also have the Rook Discover running. So the Rook Discover watches for devices in these worker nodes, and if they are available, they will be added to the cluster automatically. The agent pods, the Rook agent pods will manage the Kubernetes storage events, and the CSI plugin will manage the provisioning, attaching, and mounting volumes. And as you can see here, like we can have the actual disks within the Kubernetes cluster or outside. It doesn't matter, because now you have these pods that can be talking to a remote machine that has the actual logical device attached. So it's very powerful. And here are some code snippets from the actual deployment of these different components. So here's a Rook, the Rook operator. You run this. First, you need to apply some RBAC permissions, which is also a YAML file, and then you apply this, and it installs Rook. And it takes around 2 minutes. And then you install Ceph, and in this case, we have 3 as the number of monitors, and since the monitors are responsible for maintaining the cluster membership, you need an odd number and not too many monitors. So the optimum is 3, the recommended number. And then you apply this to another Kubernetes definition to create the Ceph-FS file system. And in this case here, I'm using 3, the replication of 3, for the metadata layer and for the data pool layer. So we have for each data that's being persisted to this storage cluster, it will be replicated to the 3 worker nodes that I deployed previously. And here's the installation of the Ceph-FS plugin itself. So as I mentioned before, we have the attacher that is watching for the Kubernetes volume attachment objects. The provisioner is watching for the persistent volume claim objects. And the register is actually registering the driver with the kubelet through a Unix socket, which is the interface that's defined by the CSI plugin. And here's the timeline. Since I'm not going to show like the whole thing, I'm going to show only like a demo of the Jenkins cluster running and being able to work with the Jenkins cluster, even if the master node with the disk is down. But basically, it takes 2 minutes to run the RBAC and install the operator. Is basically pulling Docker images. And then the Ceph installation takes more time, because when you create the cluster will see 3 worker nodes, and then it will format the disk. In this case, I'm using ext4 file system, and it takes like 8 minutes on each node. And then you install the plugin, which takes about 2 minutes just to download the image. And then to install Jenkins itself, I'm using Helm. So it's a Helm install, and it takes around 3 minutes. So let me show the recording of this demo. 1 second. So here I have, let me go back. So here's the Ceph dashboard. So I have, as I mentioned, 3 monitors, 3 OSDs, as you can see on the up right corner, and it's in healthy state, and I have 76 objects there. So I'm gonna run a Helm install Jenkins, pointing to the official Jenkins stable chart, Helm chart, and I have like this chart configuration, which is on this this repo, this GitHub repo that I'm gonna share with you guys, and I made it open source. So you can do all of this that I did at home, and it's pretty fun. So let's install Jenkins. So now this is the output. You can run this and see the URL, but it takes some time, so it won't be available. But as you can see here, the new files, so Jenkins is being deployed, and I'm using this shared file system to store all the data from the Jenkins deployment. So it takes around 2 minutes, so it's 114 seconds running, around 2 minutes, then Jenkins is up, and I can go create a pipeline. So I just added like a token. Now I have access to all my repos. I can point to this repo that I made open source. It has a step-by-step guide, and now all the Jenkins jobs are triggered. So basically, I had a Jenkins file in that repo, and it sees that I have 2 branches and 1 pull request. So it's running those jobs. And as you can see, the jobs are being running on the worker nodes. And for each pod, since the job has 3 stages, you have 3 pods. And they are running parallel in these different nodes. So this is the build stage. I'm basically building a Docker image. And then the publish state, I'm pushing to Docker Hub. And the deploy stage is a Helm deploy. So now, as you can see, there is a Hello Nginx application that's running on this cluster, and was a result of this. In a real scenario, you would have like if it's production, you would have a manual step saying, do you want to deploy this or not? So, but for the purpose of this demo, it's being deployed for every pull request, and for every pull request, you would be able to see the new version of this Nginx application. And I don't know if you saw, like the Nginx application is exposing the load balancer, so you can go to the URL and see the actual application running live. So now what I'm gonna do, I'm gonna stop the node where the master is running, and the master is running with like a disk attached. So if I had this, if I had done this with like our previous setup, then the Jenkins would be down, and you wouldn't be able to access and use the Jenkins until you would bring back a new node and attach the EBS volume to that new node, and then you would be able to use Jenkins. But in this case, you will see that the node will be not ready. So the Kubernetes saw that the node is not ready, but it takes some time for the actual Jenkins master to see that that node is not there anymore. And the Ceph cluster now is in a degraded mode. So you still have, if you see on the top, there is 1 OSD down, but you still have quorum because you have 2 nodes that are still up, and the formula, like if you have 3, 2 is enough to have quorum. So you still can write to this cluster. And in this case, I'm gonna wait until the Jenkins master is allocated to another node, and I will create another pipeline and demonstrate that I can still use Jenkins, and even though we have like 1 node less, and the disk is gone. So I'm still able to see the previous data as well from the previous job that I ran, and now I'm running another job. And as you can see, the jobs are being spawned on the worker nodes, and as soon as they finish, they are removed from the cluster, and the data is released. But all the logs are streamed to the master. So the logs are still stored in the shared file system. And you can see all the logs. And so this is a very lean deployment of Jenkins, and I recommend you guys to try it out. So I will now bring back. So I went to the console and I brought back the node, and now Rook will see, oh, there is a new node again. So I'm going to add that to the Ceph cluster. So as you can see, it's 3 out of 3, and then after a few minutes, the Ceph cluster is healthy again, and you can use as before. And here is just showing that you have a replication of 3 for the shared file system for both the data and the metadata layer or pools. So that's it for the demo. And so next steps. So Rook automatically exposes all its metrics through Prometheus. So I would like to add some alerts and use this as our main deployment at Docker. And I would like to also experiment with the snapshots and restore that Michelle mentioned. So it should be available at some point. So since we are using CSI, we can leverage these new capabilities as they become like GA. And another thing from Rook, so Rook will graduate this EdgeFS CSI plugin to V1 in Rook 1.1. And I think the scheduled release date is July 2019. So I would like to try this with NFS and iSCSI. And also use the Valero or Arc to take a backup of the whole Kubernetes cluster. So in that case, we can, even if the Kubernetes cluster itself dies, you have a way to restore it very easily. So we haven't tried that yet, but I would like to try it in the future. And as I mentioned, this is the URL. It's a step-by-step guide. It's a very easy to follow step-by-step guide, and you can reproduce everything that I did as part of this exercise. So, and there are also links to the things that I studied as part of this project. So we have the Rook URL there, the Ceph CSI plugin, and also the Jenkins Helm chart. That is the stable version. And it's pretty much it. Do you guys have any questions?
Yes. I saw that you have used public Jenkins jar.
Yep.
Where did you specify the BBC in order to consume the storage class for CSI?
So I specified the CephFS storage class. Oh, so he asked which storage class I specified when I created the Jenkins deployment. And I specified the CephFS storage class that I created previously, which is a share. So from the pod perspective, it's just a volume mount. But it's actually a shared file system that's running underneath this volume storage class.
But you didn't specify in the jar.
Oh, I did. Yeah, it wasn't described there, but it is there. Like if you go to the repo, you will see that I'm specifying it there. Oh, because in that command, I passed as an argument the chart values. And it's a YAML file that has all of this definition. So I have the health checks, all of this, like the image that I will use for the agent, for the Jenkins agents or workers, and that Jenkins agent, I also created like a new image that handles the difference between the Docker UID from the host and from the container. Sometimes if they're different, you cannot run Docker from the container. So that image is handling that problem as well. So it can run in any worker node, and it will make sure that the UID from the host is the same as inside of the container.
Oh, and also to add to that answer, in Kubernetes, we have this feature called a default storage class, where an administrator can define a specific storage class to be the default for the cluster. And then from a pod's point of view, then they don't have to specify any storage class. They just leave the storage class field blank, and then it will just use whatever the cluster admin has defined as the default. So depending on where you can run Kubernetes, different providers will set different storage classes to be their default. So if in your cluster someone decides they want to use Ceph as the default for everything, then it could be done that way.
Yep. There's a question there. Thanks, Michelle.
I have a question. When the node stopped and you brought it back up, did you have to do anything for the Ceph cluster?
Nope. Okay. So Rook is doing that job for you.
Okay, I'm asking because I had a very similar scenario without Jenkins,
Yep.
but it didn't recover like
Yep,
these days.
recovered. Yep.
Okay, thank you.
Welcome. We can leave it here. Yeah. Any more questions? Thank you very much.
Okay. We set the screens up. Let's maximize it.
Okay. Guys, thank you for being here. My name is Arko, and I'm a software engineer here at Docker. Today, I'll be talking about two buzzwords, Istio and ingress controller. I will not be talking about a service mesh. I'll show you how easy it is to deploy Istio as an ingress controller, and what are the cool features inside Istio that you can leverage to fulfill your ingress needs. So let's start with the first buzzword, right? What's an ingress? What's an ingress controller? So an ingress exposes services to the internet, and an ingress controller fulfills that ingress configuration. So what that means is, let's say there's a web server that's hosting docker.com. It's the ingress controller's job, which is sitting at the edge of the cluster, to accept, authenticate, and route any HTTP request for that web server to the right backend server. Buzzword number two, what is Istio? You've probably heard about this. in the Service Mesh Summit before. I'll sum it up in one sentence. Istio was built to solve one problem, offload network services from the microservices so developers could concentrate on the business logic and the infrastructure could take care of the rest. Before we dive in, let's talk about the basics. So in the layer 4, layer 7 space, the words proxy and load balancers are used interchangeably today. That's because they do the same thing, intelligent routing. So in this example, you can see that when a client performs an HTTP request, the proxy will terminate the TCP connection and create another TCP connection with the backend, perform an HTTP request on behalf of that client, and send that response back to the client. Here you can see that there's one TCP connection between the client and the proxy. Two HTTP streams are being sent, and this is being sharded to two different backends by the proxy. So I picked up this image from Matt Klein's blog about load balancers and proxies. You guys should definitely check it out. I learned a lot from it. So in this diagram, you can see a Kubernetes cluster below the dotted lines. There are two services which are connecting to two pods. Everything in blue is the data plane, and that's the path the traffic takes to enter and leave the cluster. This is also called the north to south traffic. The green is the data plane, and the entity is called Pilot. So Pilot is responsible for listening to changes in the Kube API for the ingress resources, and accordingly, it pushes the right configuration into the data plane, which is the ingress gateway. Inside the ingress gateway is the Envoy proxy that was built by Lyft. So let's take an example. Let's say you have docker.com that's being hosted by a web server in one of the pods, and Jane is trying to reach it. Jane's request would reach the edge of the cluster. The ingress gateway would intelligently route it to the right service and the right pod. CRDs are custom resource definitions. So I was playing devil's advocate before this talk, and I asked the service mesh folks, is there a way to standardize service mesh? And they didn't really have a good answer. And that's because it's very hard to express all these policies, all these traffic policies. And everybody does it differently. So in Istio, there are 3 CRDs or custom resource definitions you can use to define your traffic policies. Gateways, virtual service, and destination rule. I've drawn the arrows to basically help you visualize which rules are applied to traffic and when. So when traffic enters the cluster, it's the gateway rules that are applied to the traffic first, then the virtual service rules are applied, and then the destination rules are applied. So let's start with the first CRD, which is gateway. So the gateway rules are responsible for exposing and terminating your external traffic. So it supports HTTP, HTTPS, and TCP. For TLS, simple TLS, MTLS, and SNI pass-through are supported. On the right, you can see an example gateway resource in YAML format. It's called cluster gateway, and it's allowing all HTTP traffic on port 80 to enter the cluster. Now that the traffic has entered the cluster, it's the virtual service rule's job to route it to the right Kubernetes service. This is where you apply your fancy layer 7 routing rules. You can apply weights to do some fine-grained load balancing. You can do some path rewrites. And you can basically use regular expressions to simplify your job. So in this example, you can see that all HTTP requests with demo.example.com in the host header will be routed to the demo service on port 8080. So after you've routed all your traffic to a service, you can apply additional policies on this traffic. These could be traffic shaping policies, particular load balancing configuration, or even outlier detection policies to enable custom health checks. So I know that was a lot to take into, but I'm going to do a demo with all those examples, and hopefully things will be clear. Can you guys see clearly? Oh, yeah, great. So this is my Kubernetes cluster. Okay, it works. So you can see that I have 4 nodes. I have 2 Linux nodes running Ubuntu and 2 Windows nodes running Windows Server. Let's try and deploy some apps. Okay, so I created some deployments. You can see that I used the Docker demo image to create multiple deployments. There's a version v1 deployment, which has a replica set of 4. There is a v2 version with 1 replica. There's a v3 version with another replica. I also created some Windows pods with 3 replicas. Don't have my IPs yet. I can see some IPs now. So let's see if the pods can talk to each other. Because in Kubernetes, it's a flat network. So let's try and ping a Linux pod from a Windows pod. Oh, sorry, vice versa. Cool. So networking works. That's great. This is not a disaster. Not yet. So I have created this YAML using Helm. So I pretty much disabled all the options, and I only enabled pilot and ingress gateway. So you saw in the previous diagram that we only need 2 components, one control plane component, which is pilot, and another data plane component, which is the ingress gateway, to create an ingress controller in Kubernetes. So let's see. What got created. So you can see that there are 2 ingress gateway pods and 2 pilot pods. 2 because I'm paranoid and I like HA, so if one dies, another one is always there to take care of my traffic. There is a service of type node port. So what I'm doing is I'm exposing a high order port, which is 32,000, and I'm forwarding all my traffic to port 80. Now that I have my apps running, I have these controllers running, let's try and reach this cluster and the web servers that I just deployed. As you can see, I cannot connect to my cluster. That's because the gateway is not accepting any traffic, not yet. So let's look at a simple rule. So in this example, you can see that when I apply this, all traffic on port 80, coming into port 80, will be accepted by the cluster. And if the host name is demo.example.com, it will forward all this traffic to demo service. And you can also see that virtual services are linked to a gateway. Like I said, the gateway is, when you're thinking of applying policies in your network, think of gateway first, virtual service second, and destination rule last. Let's look at a rule for Windows as well. So it's a similar rule. The only difference is when the host name is windemo.example.com, it will forward all traffic to the WinDemo service. Great. Now that I've deployed those resources, let's try and connect. Great. So I basically triggered an HTTP request using curl. The IP 40.118.239.50 is the IP of my external cluster. Like I showed you, I used node port to expose a high order port. And the ingress controller and pilot did all the magic, and it routed all my traffic to the right backend server. You can see that the response that I got back is in JSON format. I basically got the host name. I got the version, which is a label and an environment variable that I added when creating my deployment. And I got some metadata as well. So let's try and see if we can connect to the Windows deployment. Great. So I changed the host header. And now you can see that I can reach my Windows web server, which is an IIS web server. The way I did this is all my Istio controllers are pinned to Linux nodes. And those are the entities that are intercepting all the traffic, and they are creating an HTTP request to the backend server. So you don't, today, Istio and Envoy are not supported on Windows, but this is sort of a cool workaround to still have a mixed node cluster and use Istio as an ingress. So let's take another maybe complex example. So if you look at the virtual service rules in this example, you can see two things. I'm saying that if I have a custom header stage with the value dev, then I want to basically route all my traffic to version v3 of the demo service. And this is this is sort of a canary deployment where when you have a new deployment and you want to route special traffic to this web server, this is a simple way to do it. For the rest of the traffic, what I'm saying is I want 80% of my traffic to go to version v1, and I want 20% of my traffic to go to version v2. And I'm using this paradigm called subset, which is an Istio construct, to do this. What it's doing is I am saying that I want a subset of the deployments. I want my traffic to go to a subset of the deployments. And so I'm using this thing called subset v1 in my virtual service rule. And then if you look at my destination rule, this subset v1 matches the version v1 label. And the subset v2 matches the version v2 label. So let's try and apply this. One thing to note is I showed you before that I had 4 pods of version v1, and I had 1 pod of version v2. And my weights that I'm using is 80:20. So ideally, if I send 100 HTTP requests, it should be spread out equally between all the different pods that I have. Let's open my cheat sheet. I could just do this myself. That's kind of accurate. So if you can see, each pod, and you can see they're all different host names, are receiving approximately 20 requests. So load balancing works at such a high, fine-grained level. I have one last example before I head out. So I want you to not look at the virtual service and the gateway, but concentrate on the destination rule. Using this rule, I am requesting, or I'm telling the proxy to add an HTTP cookie into the response that is sent back to the client. And when the client sends an HTTP request to me with the cookie, I want to hash on this cookie. And so what that does is my bucket will always be the same, and it'll always go to the same backend server. And this is the way operators usually achieve sticky sessions. So I apply the rule. And so if you look at this example, you can see that there is a cookie that has been added by the Envoy proxy. Let's try and run this command again. What you'll notice is that the cookie value has not changed, and the hostname value has not changed. And that's because the proxy is hashing on this cookie to send the traffic to the same backend. I also had another example where if I added a custom header, I should reach version v3. And there you go. Oh, this is WinDemo. My Linux app is called demo. Yeah. So I added a custom header into my HTTP request, and Ingress Gateway did all the magic since I requested it to, and my traffic got routed to the version v3 deployment. So that's kind of all I had for today. What I showed you was how easy it is to deploy Istio as an Ingress controller. What are the cool features in Istio that you can leverage? And when you think of leveraging all these cool features, where should you apply it and how to apply it? These are all the links I use to learn about Istio. You guys should definitely check it out. Thank you. I'll be happy to answer any questions if you guys have any, and if you have time. Do we have time? Yeah. Yes. Can you say that again, please?
The sticky session, what happens if the host goes down?
That's a good question. So if the proxy receives some 503s, sorry.
In the sticky session, what happens if that host goes down?
Yes. So if the host goes down, I believe it will. I'm checking this, but if you have specified the right outlier detection configuration, the gateway can basically redirect that traffic to another backend server.
But if you had a session, then you won't have the state, will you?
That's right.
So it'll be an error for the user?
So I added, yes, but so coming back, I added a TTL of 60 seconds. And so that session will probably end after 60 seconds. Yeah, if it's not, sent again. Yeah.
Okay.
Are there any other questions? None. Cool. Thanks, guys.
All right. So can everyone hear me? So we're on the final talk of the afternoon. So I'm Deep again, and Jean Rouge, who was initially supposed to give this talk, could not make it because he's not feeling too well. So let's take a look at Kubernetes support for Windows. So Windows support for Windows workloads in Kubernetes has been evolving for a while. It was alpha in about v1.5, graduated to beta around 1.9, and finally we have GA or stable support starting in 1.14. What does that basically mean? You should be able to run worker nodes running Windows Server 2019, starting version 1.14 of Kubernetes. Docker Engine is the main container runtime that's supported at the moment. We'll go into upcoming work around containerd in the future. And the master nodes still need to run Linux. So adding a new Windows worker node to existing Kubernetes cluster typically involves a lot of steps if you want to do it manually. You need to install Docker, pull in the various Windows-based images, create your pause images, and then you have the initial setup. Next, you need to get your Kubernetes binaries and the appropriate configs to the CK directory. It can be any other directory as well. Next, you need to get a bunch of PowerShell scripts, configure your CNI, such as Flanell, manually copy several parameters, and then you have to start Flanell and kubelet and kubeproxy in appropriate fashion so that all of it comes together and the node can talk to the rest of the cluster and accept workloads that it can run. You also need to set certain annotations on each of your nodes so that your Linux workloads do not end up accidentally in the Windows nodes, because that will just not work. So there are quite a few gotchas if you want to set it up all manually, but these are in details the manual steps. There are several automated ways of doing it. There's preview support for Windows workers in the various clouds, specifically AKS. In EKS, there's preview support, and I believe in GKE, there's some work in progress. The AKS Engine tool, which is an open source tool, can generate Azure ARM templates with which you can bring up worker nodes today if your environment involves bringing up clusters in Azure. And in the open source repos, the kubeup scripts can be easily used to deploy test clusters with Windows worker nodes in a GCE environment. So let's look at some of the interesting work that's going on in the SIG Windows community. So one of the things that we have been pretty actively involved in is bringing in support for something called group managed service accounts. It's the canonical way of authenticating services on Windows platforms. So it allows your Windows workloads to integrate with Active Directory. The alpha support for this in Kubernetes, where you can actually manage the GMSA configuration in an orchestrated fashion, has been launched in 1.14. And it involves a few different components. So you need to install something called admission controller webhook that does a bunch of security checks on who is allowed to use a GMSA. You need to enable a feature gate to make sure that, since it's an alpha feature at the moment, the appropriate plumbing in the container runtime integration through Docker shim actually gets enabled. And you need to provision the right GMSAs in Active Directory and make sure your Windows worker nodes have access, has been given access in Active Directory to the appropriate GMSA accounts. And then within each Kubernetes deployment, you need to create a GMSA credential spec custom resource, which we'll look into in a bit, for each of the GMSA, as well as configure a RBAC role that allows a service account to access the GMSA. And finally, add certain annotations to your deployments, which indicate which GMSA to use for a certain pod. So here's a quick example of GMSA credential spec. It says, it lists out the specific GMSA accounts that need to be referenced, as well as domain join configuration, like what are the DNS names for the Active Directory, the GUIDs, the machine account name, and so forth. Once all of that is done, on the deployment side, you need to add certain annotations. Now, the annotations is how we launched alpha, as in just to try it out. This will be moved into full-fledged API API objects like security options in the future so that you can specify it directly in the pod spec and not as annotations. But this is how it works in 1.14. You can specify it either at the pod level or specific GMSA for every container in the pod if you want to deploy something like sidecars along with main pod that's running the job. So one interesting thing that's not kind of taken care of in an automated fashion is that as you bring up worker nodes, they need to, in order for them to be able to run your Windows workloads that require GMSA authentication, they need to be added also in Active Directory and provided access to the GMSA accounts. So if that setup is not coordinated or orchestrated appropriately, things are not going to work. So that's an important gotcha, and we are exploring how that can be kept in sync in an automated fashion. And something to keep in mind is the annotations that we just went over will be moved to proper API objects once the graduation happens around 1.15. So GMSA takes care of many of the interesting Windows existing practices around identity. So let's look at some of the persistent storage options. So there was a detailed talk around this yesterday. You can go take a look at that. But just a summary of things, of how things stand today. So entry plugins, mainly directed at the various cloud environments, already support Windows workloads. So there is pretty stable support if you want to use Azure File, Azure Disk, GCPD. There's EBS work that's in progress at the moment. In on-prem scenarios, you can have Flex Volume plugins. These are published by Microsoft. And these are essentially PowerShell scripts that you download from the GitHub account that's mentioned here. And you need to just place them in your Kubelets Volume Plugins directory, and they should get picked up. Finally, it's good to have the Flex Volume plugins that handles the mount and the attach, but what about provisioning? For that, if you want to hook up a dynamic provisioner, that's something being worked on at the moment in the appropriate dynamic provisioning directories or the appropriate GitHub accounts. There is experimental support for Target D at the moment that we are planning to work with the upstream community with, and we are also engaging with certain storage vendors like NetApp, et cetera, to see if we can have something like Trident support dynamic provisioning that allows you to specify the Flex Volume plugins as the PV source so that they can work together and you can do the full volume lifecycle through Kubernetes. The future, as Michelle mentioned earlier, is CSI support. Now, containerized, if you want to deploy your CSI plugins as within containers, which is sort of the preferred mechanism, it requires something called privileged containers. One of the main privileges that it does need is the ability of the container that encapsulates the plugin to be able to propagate bind mounts from the host into individual containers that runs your workloads. Now, unfortunately for Windows right now, that support is not there. It's not there yet. It is something that the core Windows team is working on at the kernel level to bring in at some point in the future. So what can we do before that comes out, like in the interim, right? So one option there is that we're looking into is a host-based proxy process model. The idea is you run a very thin shim as a host binary, and since it's not containerized, it can perform a lot of the privileged operations on behalf of the CSI containers and take care of some of the deficiencies in terms of capabilities that the Windows containers have at the moment. Some other work is also required around integrating with the Kubelet plugin manager so that the node plugins associated with your CSI plugins can be appropriately picked up by the Kubelet plugin manager. And this is made possible by domain socket support that was recently introduced in the Windows kernel, starting with 2019. And a final option, just to complete the picture, is also deploying host-based CSI plugins. This is not a preferred model because you're kind of getting back into a more of a distribution problem where you need to have host-based binaries in all your Windows nodes. The idea behind CSI is to have containerized plugins that do not require host binaries in the nodes themselves. So the last option is something there that can potentially work, but definitely not a preferred model from orchestration perspective. On the networking side, Arco went over some of the cool demos and the happenings there. Mainly, there is support for the overall CNI plugin model. There's also support for network policy. Flannel is sort of the broadly supported open source option. But also, there are several closed source CNI plugins that are being developed at the moment. Pretty soon, you'll hear about potentially like Docker CNI, which is one of the things that we are looking at to roll out as part of a tech preview. In many of the cloud environments, they have their own CNI modules. For example, Azure CNI is used when you're deploying on Azure. Some of the future SIG Windows work items that are being looked at is CRI containerd support. So the idea is Docker Engine is the runtime of choice at the moment, but containerd enables a few other scenarios, such as runtime class, through which you can say that you want your workloads running either as a Hyper-V isolated VM or as a container that runs as a process. So the integration with CRI containerd would enable Windows workloads to take advantage of some of those things. Next, implementation of Kube ADM support for Windows is something being actively worked on and looked at in the upstream community. We are also working on graduating GMS's support beyond alpha so that you can specify them directly in the pod specs and be able to completely or fully integrate your Active Directory workloads or workloads with Active Directory identities. There are several work streams around improving the automated testing support for PR jobs and stuff that's landing in upstream Kube. And there are also discussions ongoing around a conformance profile for Windows workers so that this can fit into the overall Kubernetes conformance conformance profiles that are already there for Linux. So if you want to get involved in the upstream community around Windows, there are SIG Windows calls every Tuesday at 9:30 a.m. PST. Everyone's welcome. Here are some of the resources. There are some pointers to things where you can get started with Windows workloads like right now. And finally, like Docker Enterprise is going to launch a Windows tech preview pretty soon, most likely in Q2. That'll automate a lot of the configuration options that we went over. One of the cool things that'll make use is this mechanism to pull host binaries as images from potentially Docker Hub and launch them as host process through containerd. And this gets around many of the constraints around being able to run privileged processes in Windows containers. And it'll obviously have inbuilt support for a CNI to enable your networking and persistent storage out of the box. So yeah, Docker loves Kubernetes and Windows, and that's pretty much all I had. So any questions? Great, thanks.